So we're into spectroscopy. And spectroscopy is the interaction between blankety and blankety. Robert, you remember?
God, what was it? I'm trying to remember if it was light and energy or light.
Oh, there's one of them. Light is energy, so it can't be, that's redundant saying light and energy.
Light and matter?
There you go.
See what happens when you pay attention to school?
No problemo. Do you see Robert? Robert's here. All right, so what is this stuff good for? Okay. Oh, we got to do the animation first. Spectroscopy interaction between light and matter. So we've got a carbon monoxide molecule, right? Shine some infrared radiation on it. Right? So interaction between light and matter. So it looks like light is a wave or a photon in this sort of thing. The light looks like a Brandy. What does light look like? Yeah, does it look like a wave or a particle? Yeah, wave is definitely looking like a particle here, but so it's sometimes it's scattering, sometimes it's absorbing it. When it absorbs it, energy gets converted into motion, right? Change the wavelength, and sometimes it absorbs, sometimes it doesn't, right? So even though it's higher energy, it doesn't. So energy is quantized at that molecular level. Well, that's something for chem. But what is this stuff good for? Whoop, I think it's down here. Okay, this is a microwave oven. Andrew, these, or A&D, sorry. Yeah? Andy, these little molecules in the microwave oven are what? Yeah, and what molecule is it, though?
Water.
Water, right? So what does a microwave oven do? Does anybody know before I turn it on? What's it do, Robert?
Causes rotation of your water molecules.
Yeah, that's what it's supposed to. Let's see if the animation does some fancy little vibrating thing. It's not energetic enough to do that. Microwave radiation is only enough to make it spin. So let's see if it makes it spin. Oh yeah, woohoo, right? So it did. So it just increases the what energy of the water molecules, Melissa? There's the K. Kinetic energy. And kinetic energy, average kinetic energy is to measure blank, Melissa, sorry, Alyssa. Blank Alyssa is a measure of the average kinetic energy of all the molecules. There's the T. Temperature, right? So they're moving really good. Look how hot it is in there, right? Okay. Electromagnetic radiation at times acts like a wave, other times like a particle. But we're going to talk about the wave nature first. It actually consists of two fields. Robert, you remember what they are? All light consists of actually two fields. They're actually perpendicular to one another. One starts with an E, the other one starts with an M. Anybody remember? Two types of fields. Electric and magnetic. Electric and magnetic are the two types of fields. Okay. Now there's a different type of antenna for each field. Now what does an antenna do? Andy, what does an antenna do? We've used the words antenna a lot. What does it do? You got an antenna on your cell phone. What does it do? What is its purpose?
It improves the reception.
It improves the reception, right? It must be picking up some signal, right, and amplifies it, and that's what an antenna does. So depending on what type of field you have, right, you're going to have a different antenna. So since we have electric magnetic fields, we need an antenna to pick up magnetic fields. We need an antenna to pick up electric fields. They're two different fields, so two different antenna. So this first antenna, type number 1, Mel, looks like it's for, all these diagrams are for it. Looks like it's for what? Yeah, the magnetic field, right? The magnetic field of light, okay? So how does it work? Okay. I think it's Brighton, I forget the state. All their power is renewable, every watt of it. And a lot of it is through making water spin this hunk of metal surrounded by magnets. What the hell? How does that work? You can get electricity from that? Right? So that's I think you have to take physics or something, but it's not too hard to understand though, because electricity, what we believe, is composed of moving what? Electrons, right? It could be charges, right? If you're talking about, you could actually get electrocuted in water, right? If it's dirty water, it's not pure, you actually have ions in there. Ions, charged particles, they're going to move, conduct electricity. So any charged particle moving is electricity. So the point is they're charged particles and they're moving. That's electricity. So will a magnetic field push around a charged particle? Yeah, they do. Electric fields push around, sorry, we're talking about magnetic fields though. Magnetic fields push around charged particles. Or charged particles can be pushed around by electric fields, however you want to think about it. So if you take a bunch of these magnets, right, and then have something that's charged moving inside it, you're gonna force these charges to move. And everything contains charged particles, right? There's electrons everywhere. You can't stop it. So take something that has a lot of electrons, probably a hunk of metal, right? Put it inside, or probably do it the other way, it'd be easier. I think this is what they do. Let's spin the magnet and keep the hunk of metal on the outside. Right? Keep the hunk of metal on the outside, spin the magnet. Man, you're going to be pushing all these electrons around, right? So that's all we're doing here is I've got this hunk of metal and then got spinning magnets inside, right? So I can generate some voltage. All right, turn it on. So you're going to have to tell me how much voltage, because I can't do all this at the same time. Yeah. But I don't think it's only going to be, well, let's find out how many volts. I don't know. So see what this is first. All right? You've probably seen these hand generators. They're great for camping because of battery. There's no battery in them, right? You just walk around and to the bathroom, wherever you're going, and spin your little thing. You can't run out of electricity, right? As long as you keep spinning it. How many volts do I have there? 10, 11? Okay, that should be good. That should be plenty, I think. We'll find out. 10, 11. Well, it has to, because they sell these things, right? With a little light bulb. Where's my little light bulb? I had a little light bulb. Oh, it's over here. Okay, oh, you guys haven't had laboratory electronics yet in here. But where are the two connections on a light bulb? The side and then that little tip. And that little tip I soldered a hunk of wire on because I can't get this thing to stick to it, right? So attach one to the tip, one to the side. Get my moving magnet, right? Woohoo! Right? So it works great. So you can have it work this way, but you can also have it work the opposite direction. In other words, you've got this magnetic field, right? So here's the one where you're actually generating the electricity. You're actually moving that magnet around, right? But do it the other way. Let's have this magnetic field coming from, where could it be coming from? You've seen these guys on like sea a lot of ships. I don't know if you watch the movies and look really, really closely. You see these weird, funky-looking antennas. Not everything is based on the electric field. Some of these antennas are based on the magnetic field and pick that signal up. So, and they're in a loop. So the signal's coming from, who knows, the Coast Guard or whatever, right? Hey, yeah, where's your ship? So you got to pick up the signal, and it picks up the magnetic field, right? So the magnetic field's traveling through here, and it induces the current. Okay, it makes those charges move, and this amplifies that signal. Okay, so this is what an antenna has to look like if it's going to detect or amplify a magnetic field. Okay. It has to be made out of metal, because otherwise there's no charges to move. Okay, it has to be made out of metal. And antenna type number 2, well, this must be for what type of field, Andy? Not magnetic, but electric. So now it looks like it's not a circle anymore. Just what, Mel?
Pole.
It's a pole. And that pole had better be made out of what, Brandy? Otherwise it's not going to work. Yeah, this antenna, it better be made out of what? Metal, right? And I bet you this guy's plastic coated, but electric fields can pass through plastic, right? So, because if it's not plastic coated, when you grab it, you're going to become part of the antenna, and then you can you change the signal, right? Change the amplification of it. Okay. There's no animation there. I have an animation here. So we have here's your radio station. And here's Brandy on the hill trying to, look at, she's got a huge antenna here, right? But how does this guy transmit his signal? A real strong hint is when we were playing around with that oscilloscope. You saw it. You saw the voltage when we spoke into that speaker, and you saw the voice. How does the voltage change with time? Man, it was really ugly and complicated. But the point is you had voltage changing with time. Well, let's just apply that same signal to this. Well, that's going to move that electron just like it did. It's going to look identical to what it looks like on the oscilloscope. How does that voltage change with time? It'll make that electric field oscillate. Well, now you've got a charge that's moving. Remember, it goes both ways. You can have an electric field push an electron around to make it move, or you can force this electron to move, and it's going to emit the electric charge. Right? It's emitting light, and that's what's going on. It's emitting light. So it's emitting light. Light is, now again, they're only interested in we're only interested in electric fields here. So, all right, notice it kind of picks it up. Right? The electrons in that antenna, they're budging a little bit. Okay? So it's enough to amplify that signal and pick it up. Okay. So whatever signal is sent over here, the exact same one is picked up over there. Okay. And again, this is what field? Electric field. All right. Hey, here's a good question, Brandy. We said this is light. Light is composed of electromagnetic fields. We don't see the magnetic field. All we're seeing is the electric field. And can you see this region of the electromagnetic spectrum? Or what region is this? We call this, all this is light, but this is specifically called what waves? It starts with an R. Radio waves, right? You can't see this stuff, right? Okay. If I oscillated it, if I got it to oscillate at, different frequencies, maybe you can get it to a region where you can see it. Let's see. So here's our wave. This is plain polarized radiation. All light, composed of this stuff. It looks like the electric field is blue and the magnetic field is red. Which direction, Mel, is this wave moving? Now, you got a lot of choices here. First, recognize the electric field is in the plane of the paper here. right? Electric field's moving up and down, right? Because that's what it's trying to show. It's oscillating up and down. The magnetic field is coming out of the paper and back in, oscillating this way. So you have one oscillating this way, one oscillating this way. So my question to Mel is, where's it going? Right? This whole wave has to be going somewhere because we saw it, right? This light moves. We know light moves. In a vacuum, 3 times 10 to the 8th meters per second. Which direction? Do you want to guess? Either it's moving one of two directions. Robert? Which way? Do you know?
I was just thinking, I remember the picture, I don't remember anything else.
It's either moving this way or it's moving this way. Right? It's definitely not moving up or down. In other words, what I'm talking about is there's motion. Light has inherent motion with oscillating electric and magnetic fields, and they're perpendicular to one another. But what direction is this whole wave moving? Well, it's either going this way or it's going that way. You can't really tell by the picture. Okay, so we just got to pick one. It really doesn't matter. Okay, so, okay, fine. You like going to the right. So let's say it's going that way. That's the point. You can't really tell, but it's going one way or the other. Well, so we picked that one. Good. Circle a single wavelength. Alyssa. Now, a wavelength is one individual repeating unit. I'm going to start circling. I'm going to start circling right here. So how far do I go? Right here? Okay, so if you take this hunk, cut it out, and paste it, you get the same thing again and again and again. No, go to the next one. She was close. Go to the next one. And you don't have to go from one end, from node to node there. You could have gone right, from this peak to that peak, right? Just a repeating unit all the time. Okay, but it's easiest to do what you're doing there. That's easiest, just to pick node to node there. The amplitude. Andy, how would you identify an amplitude? I know.
Basically, the distance between the maximum and the bottom line.
Yeah. So it's not going on forever here. There's actually an end to it, right? So you have an amplitude. Let's make it purple or something. You got an amplitude for this guy, and you got it's kind of odd to make the same arrows, but you have an amplitude here, and you've got an amplitude there. You have an amplitude for the electric field, amplitude for the magnetic field. Right. Okay. So we did that. We did them both, actually. Why is this wave polarized? Brandy, that is a tough question. Because you're supposed to know how to draw this, be able to reproduce, and what you are drawing when you draw this is polarized radiation. Well, what makes it polarized? Well, if this is polarized, what would unpolarized be? That might be an easier question, but let's just stick with this one first. Anyone know? Why is this polarized? All of just pick a field. All of the electric fields are in the same, the P word, plane. All the electric fields are in the same plane. Now you might, and this is a weird way of thinking of a photon, right? Because it's everywhere at the same time. So there's these two distinctions, right? Is light acting like a wave or is it acting like a particle? Here it's acting like a wave. Is how we're defining it. So when it's acting like a wave, when all the electric fields, for example, or all the magnetic fields, just pick one, are all oscillating in the same plane, they may not all be in sync. This is just one. The other one might be, it might be ahead a little bit, right? So it's not all in phase. Okay, but the point is, if all the electric fields are in the same, oscillating in the same plane, all in the plane of the paper here, it's polarized. That's polarized radiation. So when all the electric fields are oscillating in the same plane, that's polarized radiation. And very often we say electric field, and they're talking about electric field all the time because that's the most common field that we're going to be talking about. And you'll see why in a little bit. How can plain polarized electromagnetic radiation be produced? Okay. Is this, let's get some, where is it? Not here. Oh, here they are. They're not here either. They're gone. I thought I had them in there. Oh, here they are. Okay. Is this, here's light, right? Okay, is this polarized? Light just typically coming from a bulb. How would you know? I mean, it's not polarized. The only way to know is to see, well, I'll show you, but the only way to know is really to figure out how to generate polarized radiation. Here's one way. Make glare. Because then the light is bouncing off this thing, and you can kind of see it, I don't know, like on a road or whatever, right? You see, or on a lake is perfect. You see that's why it's so hard to see the little fishies, right? Because you see the glare. That is polarized radiation. It's coming from the sun. Sun, unpolarized, it's just totally random, and then it bounces off, and all the light that's bouncing off, the glare part, and the glare part only, it's all in the same plane. That's why it looks so glary. It's brighter. So how do you tell if something's polarized? First, make it polarized. So put a polarizer in front. And all the polarizer is doing is making all the electric fields oscillate in the same plane. I don't know which plane it is. It could be this one, it could be that one, it could be this one, but they're all oscillating in the same plane. So then you take a second polarizer. And if I cross them, well, if I have them both going in the same, the transmission axis is the same, you're not going to be able to see jack, right? But if I cross them, have one, imagine going this way, the other transmission axis going this way, what are you going to see? Anything? Can anything get through?
Isn't that kind of like with the sunglasses?
Okay, we'll be getting to that, right? First, let's line them up. Here they're lined up. Nothing happened, right? Cross it. You can kind of still see something, all right? You got to get them perfectly crossed, and it goes black. What's interesting, what I think is the most interesting out of this, is something very simple. This is unpolarized radiation. So that means it's oscillating in all the different possibilities, right? Here I put one axis through, so now it's all oscillating in one plane. That's getting out. What percent of intensity is actually reduced? What would you guess? And it's awful. It still looks awfully bright, doesn't it? So before you witness this, I would have guessed 2-3% or something, because it's like only the polarization that has this alignment should get out, but it's exactly 50%. Exactly 50%. That's a quantum mechanical phenomenon. And that's something that requires a lot of talking about. And what the hell? That's wrong. It doesn't make any sense at all. It should be a lot less than 50%. But anyway, don't worry about that. So how can plain polarized radiation be produced? Use a polarizer. What is glare? Oh, let's see. I got to find glare first. Oh, that works. Yeah.
You got a little bit on your stain.
Yeah. Well, not too good, though. Maybe if I turn the lights on, it'll be better. It's hard to see. I'm trying to find glare. Okay, I see glare. I had a good spot where you can see glare. Okay. These are, and because I got to get you to line up and look at this. And a good spot is glare is right there. Okay. So these are Babe Winkleman sunglasses. Do you remember the Babe Winkleman story?
Unfortunately,
My brother-in-law, big fisherman in Minnesota, right? Babe Winkleman has his own TV show, and it's about bass fishing. So brother-in-law watched it all the time. And then he's out fishing one day, and this boat, you know, with a nice, beautiful speedboat. Babe Winkleman's not even in there, but it's plastered on the side, flying up to him. He can't even hardly stand. And the guy says, "Hey, are you catching anything?" He's scouting the areas for Babe Winkleman. And Bruce got so pissed that he gave me his Babe Winkleman sunglasses. So he doesn't watch anymore. The point is you want to see little fishies. Do you have to buy Babe Winkleman sunglasses? Or just buy what? Any polarized sunglasses. Okay, so come on up here and see this. Okay, so what glare, so what I want you to do is come over here and see this. So I'm going to give you the sunglasses and tell you where to look. So right now I see, if you stand right here, I see this white stuff on here, glare. So you're in a different location. You have to stand over here, and you'll see the white glare. So you stand over here, and then you're going to see glare, and that's just polarized radiation because it's glare. It's polarized in the plane of the table. You put these on, the glare's gone. The glare's gone because this transmission axis is like this, right? So if I want to see the glare, I see the glare, right? Because then the transmission axis is lined up. So that's what I was doing. So try it. So you got to stand over here, first see the glare, and then put them on. The glare should go away. And then rotate your head, comes back,
yeah.
right?
Yeah.
Everybody's going to talk now.
I'm going to see the glare first. I guess for sure. Oh, well.
Yours should be polarized.
What?
Your sunglasses. Most sunglasses are polarized because it removes the glare off the road. Oh. Yeah, you got to be able to pop it up so then you can do your little ties and get the fishies off and stuff.
That's why I have to pin over your regular glasses. Huh?
Oh yeah, that could be.
That's a big thing.
Okay, so we got the glare story down. What is an electric field? Its units are volts. What's a volt? This is probably more information than you need, but it's energy per unit charge. It's a joule per coulomb. I think this is more info than you need, but that's okay. That's what a volt is. An electric field is just going to be different amounts of energy in space, right? Different amounts of electrical potential energy in space. And what's this electrical potential energy thing? Just kind of think of if I have a plus and a minus charge, they attract or repel. Plus and a minus charge, they attract. So there's electrical potential energy. Plus and a plus, they repel. There's electrical potential energy. Okay. So whether your little charge is attracted or repelled just depends on its charge. Which of the fields of light interacts with matter for most types of spectroscopy? Andy, you've got a 50-50 shot at getting this right. Electric, exactly. Okay. What would you guess here, Brandy? Which field interacts with matter with NMR spectroscopy? And actually, it's NMR. I can't think of any other spectroscopy. Which field is it? Magnetic, because most everything else is electric. So, magnetic. And we'll talk about that when we get there. What is the difference between monochromatic and polychromatic light? What do you think, Mel? Flashlight. Mono or polychromatic? Give you a hint. Oh, how do I get this to work? I can't get it to... Yeah, I'm trying to get all the colors, right? So this flashlight is poly, more than one color. Maybe because I got this focused wrong. You can kind of see the colors there. There, it's better. A little bit, maybe. Okay. So mono, one wavelength. The electromagnetic spectrum. Okay, Alyssa, name a region of the electromagnetic spectrum, and we'll just slap it on the spectrum here. Any region. Randy mentioned one. Radio waves. Okay, would you say that's kind of on the high energy side, Robert, or on the low energy side? Radio waves.
Probably go with low.
Low energy side. So I'm going to write radio waves over here. Okay, so low energy, I'm writing on the low energy side. Another one, Andy, another region of the electromagnetic spectrum.
IR.
IR. Is that a little bit higher or lower than radio waves? Higher. Yeah. IR really stands for what? Anybody? Infrared. And what's the layman's term for infrared? You buy the little, and I want these so bad, those night vision goggles, but they're so expensive.
How badly do you want them?
How?
Get you nod for $200.
That's so expensive. What's the layman's term for infrared? Starts with an H. HEAT? Heat. Infrared is also known as heat. Okay.
Worst game of thing, man.
Another region. Brandy. Ready? Microwaves. All right. Where would they go? Let's do microwaves last. There's a reason why. So let's not add it yet. What else? Gamma rays. High energy, low energy? High. Really high, man. That's that stuff that comes out of, like, what, supernovas and stuff. How about the type of radiation that it can go through skin but not through bone? Ultraviolet's another one. That one will give you sunburns, but let's do this one first. It can go through skin but not through bone. It's just not energetic enough. If you break something, you're going to get one of these. X-rays. Okay, the sunburn stuff, ultraviolet. Where would that go? Yeah. All right. How about the name of the guy that has all the colors that your eye can detect? Roy G. Biv. Because you can't see any of this stuff yet, right? But there's a hint on this. Do we write, see what I'm saying? Because this is low energy to high energy. So do we write Roy G. Biv, or do we write Viv Oiri? There's the hints on here. Yeah, low energy is red. Another hint is you've got infrared and you've got ultraviolet. So, Roy G. Biv. And it should be really narrow, right? Okay. So that's enough. That's enough. Let's do microwaves now. And remember, microwaves, man, you can burn your finger in there. They coffee, all this stuff, right? Cell phones operating on microwaves. Where would you put it? Low energy. Okay, more specifically. After radio? Radio waves, maybe we should do this part first. Low energy is low or high frequency. You my PChem people? Low energy is low frequency and very long, big wavelengths, right? So that means over here you're going to circle high and low. High energy, high frequency, very short wavelengths. Okay, so this is on the order of around, I don't know, starting around yards and bigger, right? And then this is on the order of nanometers, 10 to the negative 9 meters. So now we're talking about the size of, right, like molecules. Infrared, we're talking about pretty much like 10 to the negative 6 meters, a micron. So we're talking about like a hair or so. Take a hair and maybe slice it up a little bit. But on that order, microwaves on the order of, you've looked at your microwave oven, right? To see, there's a metal screen in front. And there's little tiny holes. How big are those holes? They're pretty tiny, right? But so they're just smaller, just barely smaller than microwaves. Because they wanted to max out that size so you can actually see through there and see your stuff cook. So microwaves on the order of a centimeter. So that means microwaves would go between what and what? Radio and IR. In the order of centimeters, 10 to the negative 2 meters. Okay. I always thought this was interesting. This is my last thing to show you here. So I didn't put these in the recycling bin after paying $13 to see my 3D movie, right? So didn't take them off. You go in the bathroom to do your thing because you're sitting there for 4 hours without doing your thing, right? And then I walk in there and I notice this. This is crazy. How do you tell you're wearing these glasses? The polarization here is not the polarization I used here. This is plain polarized radiation. So the polarization is right in a plane. These are circularly polarized radiation. What is it? You have to think. The pictures can explain it better than I can try. But the point is you can circularly polarize light, and that's what's going on with these. So how can you tell? You go in the mirror and you look at yourself. Okay, now I want you to do this. You go in the mirror and you look at yourself. Oh, right? And then you cover one eye, and the other one goes black. Cover the other eye. It goes black. That's the only way to tell. It's crazy, right?
I tried using those 3D glasses with just one contact on. Impossible. I can't see anything.
Yeah, you need both. Yeah. Isn't that crazy?
How did you come up with this? You're just in the restroom.
Yeah.
Why wouldn't you take this off while you leave?
Well, it's kind of like in the lab, right? They're comfortable.
Oh my god.
It's okay, I have 3 pairs in my car.
3D glasses?
Yeah. Well, paying out $13.
Jeez. You're going to keep those $13 glasses whether you need them or not.